In this video, I'll be solving the first part of fourth question of UPSC Civil Services Mains 2023 Statistics Paper 1. So what is the role of properties of completeness and sufficiency in statistical inference? And we also have to find out the UMVUE of theta for a uniform 0, theta. So first, like sufficiency. So sufficiency, if we take so we say a particular statistic, so a statistic t of x. So this is sufficient for this parameter theta. So if the conditional distribution of the sample x given t of x is not dependent on this theta. So that means like a sufficient, so generally like this sufficient statistic compresses the data without this loss of information about this particular parameter theta. So we can use factorization theorem to find this sufficient statistic. So basically the sufficient statistic reduces our dimension in the inference problems. So we can just explain those all things as a part of role of sufficiency. Now if we come to this completeness. So completeness, so a statistic t is complete if like we are having expectation of z of t is 0 for all theta. So suppose like if this is happening, so that means the z of t is 0. So let me complete. Like suppose a statistic t is complete for a family p theta if there exists a function g such that expectation of g of t is 0 for all theta, then we'll be having g of t is equals to 0 almost surely. So like completeness is a unique property, and also it ensures that the non-zero function of t has identically 0 expectation. So why does this both matters? So this both matters because of the Rao-Blackwell theorem. So the Rao-Blackwell theorem says that, so if we take any unbiased estimator, like given any unbiased estimator u, the conditional expectation of u given t, where t is a sufficient statistic, so this has less variance than that of u. So if we consider the variance of u, so that is less than or equal to variance of expectation of u given t. So basically if t is complete and sufficient statistic, then any unbiased estimator, so if t is complete and sufficient, so any unbiased estimator of t, so any unbiased estimator, any function of t will be UMVUE of our parameter. So therefore like sufficiency reduces our like dimension, and completeness guarantees the uniqueness. So hence like we'll be having an optimal UMVUE. So now like we are asked to find for a uniform 0, theta, we need to find out like uniformly UMVUE of theta. So for that, like, so basically UMVUE of theta for this x1, for x1, x2, and so on xn following IID uniform 0 theta. So that means if we consider the joint density here, so the joint density will be like for 0 less than xi less than theta, the joint density would be 1 by theta to the power n, and we also have to ensure that the maximum value should be in between the 0 and theta. So that means if I consider t, so by using factorization theorem, we can say this t is equals to the nth order statistic is sufficient for theta. So if we are having 0 less than t is less than theta, so if we have to find the distribution of this t or distribution of this nth order statistic, so ft of t is probability of t less than or equal to t. So that is nothing but t by theta whole to the power of n, because every x1, x2 and so on xn all should be less than or equal to this t. So that means if we find the density, so the density would be So d by dt ft of t, so that is nothing but n into t to the power n minus 1 theta to the power n. So we can also rewrite this thing as n into t by theta whole to the power n minus 1 into 1 by theta. So if we consider so that means this t by theta is having the density some n into u to the power n minus 1, and this 1 by theta will, like, so basically when we substitute u is equals to t by theta, du will be this 1 by theta d theta. So this 1 by theta will account for that du. So therefore this t by theta has a density u into n into u to the power n minus 1 on this 0 to 1 interval, because 0 is less than t is less than theta, so t by theta will be in between 0 and 1. So that means so n to the power, so that means like this is following beta n comma 1. So the distribution of t by theta is beta n comma 1. So if we find like expectation of z of t is 0, so that means, so to check the completeness, this is nothing but expectation of z of t, and this is nothing but 0 to theta z of t into n into t to the power n minus 1 by theta to the power n dt, which is nothing but n by theta to the power n 0 to theta z of t into t to the power n minus 1 dt. So suppose like if this is a function of theta, we can see this is a function of theta. So this is 0 for all theta greater than 0. So that means if I do like phi dash of theta, that also must be 0. Now phi dash of theta is like differentiation of this function. So that is nothing but theta to the power n minus 1 into z of theta by using Leibniz rule. So that means theta can't be 0, so z of theta must be 0 almost everywhere. So therefore we can say t is complete. So now like we got t is complete, so and sufficient. So we can find expectation of t. So expectation of t is 0 to theta t into n into t to the power n minus 1 by theta to the power n dt. So that is n by theta to the power n integral 0 to theta t to the power n dt, which is n by theta to the power n t to the power n plus 1 by n plus 1 from 0 to theta, which is nothing but n by theta to the power n theta to the power n plus 1 by n plus 1. So that means expectation of t is n by n plus 1 theta. That means it is biased downwards. So we can make it unbiased by multiplying. So n plus 1 by n, t is nothing but theta. So that means the UMVUE is nothing but n plus 1 by n into t, which is nothing but n plus 1 by n into nth order statistics. So this is unbiased, and this theta hat is a function of complete and sufficient statistic t, which is x of n or nth order statistic. So by Lehmann Scheffé theorem, it is also unique UMVUE of theta. So that's it for this video. We'll meet in the next video.